This video will try to solve a complicated trigonometric equation. We will try to find the unknown in the expression. You could use any of the identities that comes to your mind. I showed you somewhere around 25 to 30 identities in the classroom. However, here my goal is really to also show you that sometimes even if you forget your trig identities, you can still find ways to solve it if you only remember one or two identities. So let's get going. So this is the question that we will try to solve. It's this expression here. So cos of x minus sine of 2x minus cosine of 3x equals to 0. We need to find all the values of x that would make this expression equal to 0. We won't look at it in 2 pi m revolutions in different revolutions. We'll look at it in one full cycle, one full around the circle, one full revolution. We'll exclude 2 pi. So 0 and 2 pi, they get to land at the same place. So we'll look at it from 0 to 2 pi excluded, or from 0 to 360 degrees excluded. You could do your analysis with degrees or radians, doesn't really matter. At the end, you'll see me here interchange between both. Whatever you feel comfortable, do that. And also on the exam, well, it depends on the questions, what type of answer it's going to be described in the question. If you're not told find it in degrees or radians, well, do it whichever way you prefer. So this comes, like I said, from this book, from the mechanical and electrical engineering school textbook that we have for our School of Engineering, and I found this on this page 545. There are other questions that are interesting, but quite honestly, this one struck me as more interesting because it seemed slightly difficult if you don't necessarily remember all your identities, but only a handful. So here I'll try to solve it using only this simple identity that we know from the unit circle and Pythagoras law that we applied to find a specific point around the unit circle, and also the sum and difference trig identities. So this one here that I think many of you already know, and of course I showed it to you among all the other 25-30 identities that I showed. So we'll just use these two and see if we could somehow find a solution to all the x's within this range for this expression. Okay, so let's begin solving this problem. So let's see what we have here. So if you notice that maybe what we could do is tackle this expression, sine of 2x and also cosine of 3x, and have it in some term that with simply an x. So maybe what we could do, like maybe I mentioned earlier, is apply the sum in difference identity, and in this case we could just apply the sum identity. So I could think of this as such. So let's focus on this one as a first step, and then we'll focus on this one as a second step. So we could do the following. We could simply write sine of 2x as sine of x plus x. And again, if you know your identity and you could go a bit faster with these steps, you don't need to use the sum identity. If you already know what to do with the sine of 2x, go ahead, do that. But here I'm assuming that we forgot it and we only remember these two key expressions that we know from sum and difference identity, because they're very critical in different engineering disciplines, including in wireless communications and others. So let's give it a try. So this becomes sine of the first angle, so x, cosine of the first angle, so x, there's a plus, so we also put a plus here, cosine of the first angle, so it just happens to be x, and sine of the first angle, which is also x. So this clearly adds up to simply 2 cosine of x, sine of x. So that's great. It's a nice result. So let's put it in a box because we'll need to use this result later on in the expression. Next, what we could focus on is look at the cosine of 3x expression, cosine of 3x. So here what we could do is we could kind of do the same idea, break it into two pieces. So maybe write it as x plus 2x. X would be a first angle, 2x will be a second angle. And again, from the sum in difference identity, in this case from the sum trigonometric identity, we could write it as cosine of the first angle, x, cosine of the second angle, 2x, and then because there's a plus, we would write minus sine of the first angle, so x, and then sine of the second angle, which is 2x. At this point, well, let's see. We do have this expression, so maybe I could put them in red. So we have this expression that has a sine of 2x, and we also have this expression with a cosine of 2x. For the sine of 2x, well, we already found it, so we could somehow also use it here. As for this one, well, we need to work the details for this guy, for this one here. So let's give it a try. Let me just put a star. So star. So cosine, and then let's just work for the details for that. So cosine of 2x. Well, it's the same thing as writing cosine of x plus x, which is the same thing as writing cosine of the first angle, x, cosine of the second angle, x. We're doing a plus, so we put a minus, sine of the first angle, x, sine of the second angle, which is also x, and therefore you could also notice that this equals to cosine of x squared minus sine of x squared. And so this is a result that we could plug in the cosine of 3x expression, and hopefully this will help us to simplify this expression a bit, or at least put it in terms that look more or less identical. So now what we could do is we could update our cosine of 3x expression. So let's do that. So update cosine of 3x expression. So cosine of 3x is now equal to cosine of x, and then we multiply it with cosine of 2x, which happens to be cosine squared of x minus sine squared of x minus sine of x multiplied by sine of 2x, which is simply 2 cosine of x sine of x. Okay, so now what we could do is let's just multiply the cosine to the bracket and the sine of x to the bracket and see how we could simplify this, hopefully. So we'll have cosine cube of x minus cosine of x sine squared of x, and here we'll have a minus 2 cosine of x and then sine squared of x. Now, of course, I think it's easy to notice that this expression and this expression can be combined. They both have a cosine of x sine squared of x. So let's just do that. So it would be this. We will get cosine cube of x minus 3 cosine of x and then sine squared of x, like this. And this is what we were able to do for cosine of 3x. So now the key result that we got in this slides are here for sine of 2x and cosine of 3x. So for cosine of 3x, we found this result. So now every expression that you see has only an angle x. It doesn't have an angle 2x or 3x. So that's good. And then also here, every expression that you have has an angle x, not an angle 2x or 3x. And hopefully this will be something that could be helpful to find the result. So let's move on to the next slide and merge these two yellow box results in the original expression. Okay, so let's just remind ourselves the key result. I'm going to just write it here and then we'll plug it in the expression. So we found that sine of 2x is equal to 2 cosine of x sine of x. And we also found that cosine of 3x is equal to cosine cube of x minus a 3 cosine of x sine squared of x. So let's put these two results in the original question and see how it's going to look. So cosine of x is unchanged. Now we put a minus 2 cosine of x sine of x minus, so this means because there's a minus, I have to put a minus in every term, a minus here, which becomes a plus, and that's that. So let's just do this this change. So minus cosine cube of x and plus 3 cosine of x sine squared of x. So at this point, well, we could also, let's not forget that this is equal to 0. So let's see if we could simplify this. There's some commonality here. So this expression has a cosine sine squared of x. In here we have no, there is no commonality. Sorry about that. I thought there is. So we can't do that. But what we could do is the following. There's a cosine. If you notice, there's a cosine in every term. So what we could do is there's a cosine here, there's a cosine here, there's a cosine here, there's a cosine here. Maybe what we could do is factor the cosine. Sine is not in every term. There's only a sign in this expression, and there's a sign in this expression. But cosine shows up in every term, so maybe that's a good step that we could do here. We could factor the cosine of x like this. Let's open a bracket, and then we'll have 1 minus 2 sine of x, and then we'll have minus cosine squared of x plus 3 sine squared of x, close the bracket, equals to 0. Now at this point, be careful. Do not divide both sides by cosine of x and get rid of cosine of x. This is like when you deal with a parabola and you have a quadratic expression. You don't divide by when you factor an expression, you don't divide it by that expression. If it has a variable, you want to keep it because ultimately you want to make this expression equal to 0 and find the zeros of the equation. So you don't want to divide by cosine of x. You want to keep it. Let's keep it on the left, and we have a 0 on the right, and we have this big expression in the bracket. Let's continue the analysis here. So what can we do? Maybe what we could do is the following. Let's apply what we know from a unit circle. So we know that if I have cosine squared of x plus sine squared of x equals to 1, or else I could also write it as 1 or sine squared of x is equal to 1 minus cosine squared of x. Now this is an expression that I could certainly apply to here, to this expression, this minus cosine of x and the 1, merge them together, and then make them essentially this would equal to sine squared of x. So let's just do this change and see how it's going to look like. So we'll have a cosine of x outside. We keep it there. We will, instead of 1 minus cosine squared of x, I could simply write it as sine squared of x. I still have my minus 2 sine of x, and I still carry the 3 sine squared of x, and everything is equal to 0. So at this point, notice that the following, well, certainly I could add this sine squared of x with this 3 sine squared of x. So let's see how now it's going to look like. So we will get cosine of x, and then we'll have a 4 sine squared of x minus 2 sine of x equals to 0. So I have a sine of x in both terms inside the bracket. So maybe I could factor one of the sine of x outside. And also there's a 2 and a 4. Maybe I could factor the 2 also outside. So let's do that. So I'll end up with 2 cosine of x. I factor a sine of x, so sine of x. And what I have left in the bracket is a 2 sine of x, like this, minus 1, like this, equals to 0. I could divide by 2 on both sides. So let's just divide by 2 so we get rid of it. 2 is just a constant. 2 I could divide. Everything else I cannot divide by that, but 2 is a constant, that's a scalar, so I could divide by that. So let's get rid of it. So now the expression that I need to focus on is simply cosine of x, sine of x, and 2 sine of x minus 1 equals to 0. So this looks much nicer than the original expression that was given to us. So the original expression was what you see above. This was it. So we have a angle x, angle 2x, and angle 3x. Whereas here, everything is with angle x, and angle x. And all these terms is equal to 0. So what this means is that, well, what we could do is we could, again, we could simply use what we know from algebra. We just make every term that we factored equal to 0, because every term could bring this expression to 0. So we could say that cosine of x equals to 0. Another thing that we could observe, well, sine of x could also equal to 0. And then we could also say that 2 sine of x minus 1 equals to 0. This last expression, well, if you isolate for sine of x, well, it's going to be sine of x equals to 1 over 2. So now we need to solve for what possible values of x can bring us a 0. What possible values of x can bring us can make sine of x equal to 0, and what possible values of x can make sine of x equals to 1/2. So let's find that and put it in here. So maybe what we could do is we could focus on this on the next slide. So what I'll do is I'll just highlight this, and the next one, and we'll work the details over there on the next slide. So the analysis of this trigonometric expression gave us the following, that cosine of x equals to 0. Sine of x can also equal to 0. And finally, that sine of x, if it's equal to 1/2, it will also make this expression 0. So now we were curious to know what angles can give us a 0. So you could, of course, use your calculator and do the arc cosine, arc sine, and get the results here. But we could also look at the unit circle. So this is a unit circle that we have. So this is a unit circle. It's called a unit circle because it's just a circle centered at the origin, and it has a radius of 1. Okay, so when do you get x equals to 0? So x is always related to the angle that you have here. So this is cosine of the angle, and this is basically sine of the angle for a unit circle. So in this case, at which angle do you get a 0? Well, you get a 0 at this point. You obtain a cosine of 0 at this point here. This point will get you a 0 because it means that your x entry will be 0. And at this point, you will also get 0. So this means that you will get a 0 at this angle at 90 degrees. So don't forget, if we measure angles counterclockwise, it's positive. If we measure it clockwise, it's negative. So you get a 0 at these two angles. So this means that x equals either to 90 degrees or x equals to 270 degrees. If you want to write it in radians, you could write it as pi over 2 radians, and at 3 pi over 2 radians. Okay, now let's look at the other expression. When can we get sine of x equals to 0? Well, sine of x equals to 0 at this angle here and at this angle here. So let me just identify it. So you get it at the 0 angle, but you also can get it at the 180-degree angle. So at the 0 angle here, so you're just not moving, and at the 180 degrees. So here you get it at x equals to 0 degrees, or at 180 degrees. Or if you want to write it in radians, you get it at 0 radiant, or at pi radiant. Both of them will make sine of x equals to 0. Okay, so let's just circle it as well so you can see that these are the 2 points where your sine of x is equal to 0. So don't forget, sine of x is always associated with the y-axis. So at these 2 points, your y-axis is 0. And at these 2 points here, your x-axis is 0. Okay, and at these 2 points, your y-axis is 0. Okay, now let's move on to the third expression. Sine of x equals to 1/2. So you could use your calculator, or you could use your hand rule to remember how to find what a half when we get sine of x equals to 1/2. So if you remember the hand rule, you have to close the second finger of your hand from the bottom, and you count the number of fingers that are open from the bottom. So in this case, it's just 1. Square root of 1 divided by 2, which means that it's 1/2. So it happens at 30 degrees. So at 30 degrees, this is where you have sine, that is, so this height here is 1/2. It's 1/2. And this means that even at this point, you will have a, you will also get a half. So this happens at the angle 30 degrees. And you do the mirror image with respect to the y-axis. So you do 180 minus 30. So it also happens at the angle 150 degrees. Okay, so let's do that. So x occurs, you get a half when x is equal to 30 degrees. You also get a half when x is equal to 180 minus 30, so 150 degrees. If you want to write it in radians, what you do is you do 30. Well, let me just do it for you here. You do 30, you divide by 180, you multiply by pi. So 0 and 0 is canceled. So we have 3 pi. 18 is 3 times 6. So this happens, this is equal basically to pi over 6 radians. So 30 degrees is pi over 6 radians. In 150 degrees, well, you do the following. You do 150, you divide by 180, you multiply by pi, 0 and 0 cancels. 15 is 3 times 5, and 18 is 3 times 6. So the answer is really 5 pi over 6. So 5 pi over 6 is the equivalent of 150 degrees. 5 pi over 6 radians. Okay, so now we're equipped to simply write the full answer. So we got it, the full answer. We could maybe write it in a clean way. So from the smallest angle all the way to the biggest angle in one revolution. So the solution, therefore, the solution to cosine of x minus sine of 2x minus cosine of 3x equals to 0 is the following. X equals to 0 degree, 30 degree, so 0 degree is here, 30 degree is here, 90 degree, it's here, then 150 degree in here, and 180 degree in here, and 270 degree in here. And if you want to write it in radians, well, it's going to be 0 radians. 30 degrees, you could write it as pi over 6. 90 degrees, we could write it as pi. 150 degrees, we could write it as 5 pi over 6. 180 degrees as pi, and 270 degrees as 3 pi over 2. So here we have it in degrees, and here we have it in radians. Red. So let's just highlight this. Okay, and I'm going to show you on the next slide. We could also plot this and see if this is indeed the result. You could also do some sanity check or some verification. You could just plug in these values to the expression and verify, do you indeed get a 0? So we could simply do that. Let's do that on the next slide. So we solved this expression and we found the following. Let me just rewrite it. So x is equal to 0, 30, 90, 150, 180, and 270 degrees. Or if you want to write it in radians, so 0, pi over 6, pi over 2. I think I made a typo in the previous slide. I wrote pi, but it should be pi over 2. 5 pi over 6, pi, and 3 pi over 2. So degrees and radians. So now we could verify this result. We could do that. So let's just do it here. So if I have x equals to 0 degrees, well, what happens? So we'll have a cosine of 0 minus sine of 2 times 0, which is just 0 degrees, minus cosine of also 3 times 0, which is 0, which is equal, cosine of 0 is simply 1, sine of 0 is 0, and then cosine of 0 is also 1. And if you notice, this is really 0. So that's good. We could now also check this answer with 30 degrees. So we'll have cosine of 30 degrees minus sine of 2 times 30 degrees. So we'll have 60 degrees minus cosine of 3 times 30 degrees. So 3 times 3 is 9. So that's 90 degrees. Let's see what this gives us. So cosine of 30 degrees, if you remember from your from your hand rule or from the calculator, you'll find that it's root 3 over 2 minus sine of 60. So sine of 60 will, it's going to be the reverse of what you have with, so at 30 degrees you have the coordinates root 3 over 2, 1/2, and then at 60 degrees it's the other way around, so it's 1/2 root 3 over 2. So this is what you have. And then cosine of pi, well, this is just 0. So this is clearly 0, and that's good. As expected, we get a 0. Let's try 90 degrees. What happens at 90 degrees? So at 90 degrees, well, we have cosine of 90 degrees minus sine of 2 times 90. So this is 100 and 180 degrees like this, minus 3 times 90. So this is cosine of 270 degrees like this. And let's see what this is equal to. Cosine of 90 degrees, well, this is 0. Sine of 180 degrees, well, this is 0. Cosine of 270 degrees, well, this is also 0. So this gives us a 0, which is also good. So we verified this one, this one, this one. Let's go with the next one. So when x is equal to 150 degrees, what do we get? So this is cosine of 150 degrees minus sine of 2 times 150, so that's 300 degrees, minus cosine of, well, here we do 150 times 3, so 150 times 3. So this is, well, 2 times 150, well, this is 300 plus 150. So this is 450 degrees. 450 degrees is the same thing as saying 450 minus 360 because there's more than one revolution here. So 450 minus 360, this gives us 90 degrees. So we could in fact simply write it as 90 degrees. Instead of writing 450 degrees, we could write it as 90 degrees because we removed the excess revolution. It's going to land at the same place. So 90 degrees here. And that's it. Yeah, so let's give it a try. So what happens at cosine of 150 degrees? Well, it's going to be it's similar to 30 degrees, but it's going to have a negative value. So it's going to be at minus root 3 over 2. 300 degrees, well, it's similar to 60 degrees, but it's in the fourth quadrant. So sine at 60 degrees is root 3 over 2, but this will be at negative. So it's going to be, is that right? So sine of 60 degrees will be root 3 over 2. But this one will be negative. So it's going to be minus is going to be plus root 3 over 2. That's right. And then at 90 degrees, well, this is simply 0. And this gives us a 0. So that's good. So this takes care of this. Next, we have 180. Let's see what happens at 180 degrees. So cosine of 180 degrees minus sine of 2 times 180 degrees, which is 360 degrees. But we don't want 360 degrees, right? So we want to be in this range. So 360 degrees open. So 360 degrees is the same thing as writing 0 degrees. It's going to land at the same place. So 0 degrees. There we go. Minus cosine of 3 times 180. So 2 times 180 will bring us to 2 pi, or 360, which we said is 0. And then we do another 180. So it's similar to saying, well, it's just 180. Okay. So, so now what do we have? Well, we have cosine of 180, which is minus 1. We have sine of 0, which is 0. And we have minus cosine of 180, which is minus 1, which becomes a plus 1. So now we have a minus 1 plus 1, which is 0. And that also gives us a result that is good. That is, that gives us a 0 for the expression. So now finally, let's do it for the last expression, last result, 270 degrees. And let's see what we have here. So here we have cosine of 270 degrees minus sine of 200, 2 times the angle. So let me just write it here. So 270 times 2. What is 270 times 2? So this gives us 540 degrees, like this. If I remove the excess revolution, so minus 360, so I could also, this is also the same thing as saying 540 minus 360, which is equal to 180 degrees. So I could write it as sine of 180 degrees minus cosine of 3 times the angle. So well, let's write it here. So 3 times 270. So what is 3 times 270? This is equal to 810 degrees. If I remove, I think, two revolutions. So I do 810 minus 360 minus 360. So I could remove 2 revolutions here. So I could do 810 minus 360. Well, what does that give me? Well, so this gives me 850. And then I could basically also do 450 minus another revolution. And that should give me 90 degrees. So instead of writing 810 degrees, I could also basically write it as 90 degrees. It's going to be at the same place, because again, we're told that this is the feasible set of possible values of x. So let's see what this gives us. So cosine of 270, this would be 0. Sine of 180, this would be 0. And then cosine of 90, well, this would also be 0. And this gives us a 0, which means that all the results seems reasonable and seems correct, because we get zeros for all of them, and that's exactly what we wanted to see. So we in fact were able to verify the result, and everything seems correct. So everything, so all is correct, all is correct. So that's a good sign. So on the next slide, what I'll do is I'll just show you a plot of this, just to also confirm to you that what we got is indeed correct. Okay, we could also plot this just to really make sure that what we got is correct. So here, you could use any software that you want, MATLAB, Mathematica, Wolfram Alpha, whatever the case might be, okay? So here, I did that, and you see that you get the zero angle here. So this is your zero angle. So this is the plot of, so here, this line here, this is the plot of cosine of x minus sine of 2x minus cosine of 3x. Okay, so this is what this expression is. This is your f of x. Same thing here. I just zoomed it in to the expression. And if you want to make it equal to 0, so this is when f of x, this is the line when f of x is equal to 0. And therefore, you can find the zeros. The zeros are the different values that will make your function equal to 0, which is here, the 0th angle, also here, the 0th angle. So this is clearly, we can see that. You have the 30th degree, or because here I plotted it with in terms of pi. So the values that you have here are in radians, not in degrees. So let's look at it in radians. So rad here, same thing here. This is in rad. I just kind of zoomed it in. So at 30 degrees, or if you will, at 30 degrees is pi over 6. Pi over 6 is roughly, this is roughly 0.52. So 0.52 is here. So this thing here is pi over 6. This thing here, pi over 6, roughly 0.52. So this is also good. We could see a point at pi over 2. So this is pi, halfway it's here. So this is pi over 2. This is also your pi over 2 here. Pi over 2, which is roughly 1.57. Okay, we also have another point at 5 pi over 6. So 5 pi over 6 would be here. This is 5 pi over 6 radians. And 5 pi over 6 would also be here, which is, let me just write it, 5 pi over 6, which is approximately 2.62. 2.6, this is 2.5, this is a bit more, 2.62. We have another point at pi, so this is the point at pi here. This is also the point at pi here, which is roughly 3.14. And we have finally a point at 3 pi over 2. 3 pi over 2 would be here, which is 1.5 pi. So this is at 3 pi over 2 radians. In this zoomed plot, I don't have it shown, but you clearly can see it here on the zoomed out plot. This is your 3 pi over 2. And then after that, it goes to 2 pi, which is basically 0. And it will repeat itself. So we only want to see it within one cycle. So we'll just see that within one cycle. So you have all the different zeros that we expected to get. And of course, as you notice that the result is indeed correct with what we obtained. So the result is correct. So I think this is a good practice to learn as engineers to do the analysis, but also to verify your work, and using software is not a bad idea. That's it. This completes this video. Thank you for your attention.